you everyone for coming. Like Amelia said, my name is Luke. I'm a sophomore and I'm majoring in physics and math. And I have used machine learning for physics specifically before, but I've been thinking about medical applications of machine learning more recently, and I'm excited to share what I have with you. So to get started, I will direct you all to a GitHub link, which Emilio will kindly send in the chat. And I'll share my screen so you all can follow along. So this is not the right tab, but the Zoom thing is blocking where I need to go. So hold on one second. Okay. So if you go to the GitHub link, this is where it should bring you. Can everyone see the screen? Okay. Okay. So yeah, you should be here. If you scroll down, this is all of our events we've had since the inception of DSC LAM and Mary. If you scroll all the way to the bottom, you'll see our lesson for today with a short description, and then we're going to have a short PowerPoint type presentation in a moment to go over some concepts in machine learning. And then you can also find here two links for the code that we're going to be developing during the lesson today. There's an attendee version and an instructor copy. The instructor copy has everything that we're going to end up with by the end of the lesson, and the attendee version has blank spots for you to follow along and fill in. So you can open both or just the attendee version if you want to just work along with what I'm doing. I'll have the attendee version up so you guys can see like what code I'm typing as I'm typing it. So feel free to open those, or also to open the slides if you want to follow along there. But I'll start with the PowerPoint. So machine learning has kind of a lot of concepts and like theory involved with it that are kind of important to understand at a basic level before diving into the code to know what's happening. Whoops. Okay, so what is machine learning? Machine learning is an algorithm that learns from data and can build really complicated, complex, nonlinear models that take some kind of input data and can predict output data. So examples of what kind of data you might be making predictions on are, for example, today what we'll be looking at are a bunch of examples of benign or malignant tumors. And we'll have different data about the tumors, and then our machine learning algorithm will be able to predict whether the tumor is benign or malignant. Machine learning is also used in a lot of clinical trial research and also in drug development. So it's widely used in the field of medicine. More like simple textbook examples of machine learning that you might hear about are, for example, your data could be a collection of images of cats and dogs, and the algorithm could predict whether an image, if you feed it all of the pixels in the image, is that a picture of a cat or a dog? And there are other examples as well. But three main categories of machine learning that I'll just briefly mention are classification, which is what we'll be doing today, where you have some kind of input data and each individual piece of data falls in some category or class. This image is an example of, well, there are three classes. They're labeled as species here, and each dot represents a data point, and the algorithm will draw these dashed lines in effectively and categorize each data point into one of the classes. Regression is, instead of assigning each data point to a class, it'll assign a value or a set of values to each data point. So that could be like predicting what your grade on an exam will be if you study X number of hours. And the machine learning algorithm can predict that if you give it a set of examples of real world data of how that has actually played out. And a third example that I'll mention is unsupervised machine learning, which one type of unsupervised machine learning is clustering, which you won't have any labels for your data that you're giving to the algorithm. So you just have some, it's labeled here as original unclustered data, which is just a bunch of data points, and you don't really know any structure about it. You don't know like any categories or classes or values for any of the data points. You just have this data, and it will figure out a structure within the data, which here it found out, it found 3 clusters in the data, blue, green, and red. So there's some kind of similarity between those, and that could be used to better understand a big data set that you don't really have much intuition for. So the structure of a machine learning algorithm takes this form, which is called a neural network. So, whoops, sorry about that. So as the name implies, it has to do with neurons and networks of neurons in the brain, at least analogously. So here's an image of a neuron, and there are a number of dendrites, which are like analogous to these branches on the neural network diagram, and then an axon, and then like effectively other branches on the other end. And then you'll have a whole chain of neurons and a complicated network. And your brain can take in like sensory input from the world around you, feed it through this network of neurons, and then output some kind of information. You see an image of a cat or a dog, your brain can process it by feeding it through these neurons and doing complicated processing, and then you can realize that's a cat or a dog. So similarly, we don't follow exactly how the biological neural network works in machine learning, but that is kind of where the idea came from. But it's now developed to be more effective for data science applications, or in this case, medical applications. So how it works is you have this kind of graph-like structure where there's a series of layers, which here are labeled as input, hidden, and output layers. And so you'll feed your input data into the input layer, and then the data will go kind of along these lines to the next layer. The lines are called edges, and it will calculate a value for each circle or node in the next layer based on the data in the input layer, and also the values of the edges, which I'll talk about more. And then again, we'll get fed forward to the output layer where it can predict some output given the input data. And the real key to machine learning, what makes it so powerful, is that each time a new node calculates its value, it applies what's called an activation function, which is some nonlinear function. And a couple examples are here. There's a sigmoid function, which is like this S shape. There's tanh, which is another like kind of S-shaped thing. And then ReLU, which is really common and we're going to use today, which is just a linear function on the right side of the y-axis and then 0 otherwise. And if we apply these functions at the nodes, what that'll do is add nonlinearity to the algorithm, and that really allows for more powerful predictions on a more complicated data than if we just had like the value of the node is like the sum of all of the data coming into it, or something linear like that. So the goal of machine learning is to assign activation functions and weights for the edges or the lines connecting the layers to optimize this process and have the most accurate predictions on your input data. So some techniques that we're going to use today to optimize our neural network on benign and malignant tumors is first we're going to pre-process our data, which means that we're going to do some manipulation to the raw data that we have so that the algorithm will be able to train on it more efficiently and faster and with less computing power. So first, something you can do is reduce the amount of data that you're using. For example, if you have images of cats and dogs, and in every image there's like a margin or some space where no information about the cat or dog is going to be, you can just essentially crop the image and feed fewer pixel values to the neural network so that it has an easier time processing fewer data points. And another thing that you can do, which we're going to do today, is normalize your values. So if your data ranges all the way from -100 to 10 billion, it's going to be harder for the algorithm to train on that data than if you had normalized your data or scaled it down to all being like around 0 or 1 or like kind of within a small range. So the second thing we're going to use as a technique today is splitting our data set into two subsets, a test set and a training set. And we'll do about a 70%, 30% split. And the purpose of these two sets are the neural network, while it's training and updating its weights, it will only see the training set. So we've chosen about 70% of our overall data that it will see, and it will optimize the algorithm based on that data. And then after that finishes, we can test how well will this neural network actually predict on new data that it hasn't seen before by evaluating its performance on the test set, which is the remaining 30% that we haven't trained it on. So how does the neural network actually assign weights to each edge? So each line in the neural network, how does it assign a number to that that will have the most accurate predictions? What it does, at least in this method called gradient descent, is choose first just a random value for each weight, which is represented by this point here. Just which direction is going to have the steepest descent, or bring it to the minimum fastest, or so this function being plotted is called the loss function, and it's a measure of how accurate the predictions are going to be, and we want to minimize it. It could be like, one example is mean squared error, or is it called mean squared error?
Yeah, mean squared error as if you want to predict, instead of classifying, if you want to predict a continuous value. So you give me like a lot of data, and then I say here, you give me a lot of data about an elephant, and then I predict the weight of the elephant. That would be like a regression problem, and use mean squared error as your loss.
Mm-hmm. So we want to minimize that loss function by the gradient descent process will figure out which direction you can take a step to minimize it fastest. And then it will just take a series of steps until you've told it to stop. And hopefully by the end of that process, it will have gotten really close to the minimum of that function and have the highest accuracy.
If I could just step in really quick, because this bit is kind of really abstract. I really like this plot, and it's a really nice plot. If you just think about it on the X and Y axis, essentially that's like your two weights. So you have some neural network with two weights, and then on the Z axis, this height, this surface, is the loss. So where we start, where Luke kind of pointed out that starting point, it's a really high loss, and you essentially want to figure out how to change your weights and adjust them so that you can get down to a really low loss, that little minimum where the arrow is going towards. And so that's gradient descent, and it's a little weird. And so hopefully you get a little bit of an intuition there. Sorry, Luke.
Yeah, and we don't necessarily need to understand exactly how that process works, but just to get some intuition, that's what's happening behind the scenes. All we need to do is give it a few numbers, and it'll do this for us, as we'll see as we're writing the code. So there are a number of parameters, hyperparameters, that you can adjust that affect how this process is working, so that you can have it run as fast as possible and reach the highest accuracy. So the first thing we can adjust is called the learning rate, and that's just the size of each step. So it calculates the direction that it's going to take a step in, and then we've told it with the learning rate how big that step is going to be. And the reason we want to adjust that is because if we have our loss function that looks like some kind of dip, some kind of local minimum, we could take a bunch of small steps and go towards the minimum, and we will get there, but it will take more steps than if we had chosen a larger step size. But if we choose too big of a step size, we can shoot over the minimum and kind of bounce back and forth, and it might take ultimately longer to get to the minimum we want. So it's about finding a balance of how large your step size is. A second thing is called batch size. So each time it calculates the direction of steepest descent, we don't want it to use our entire data set because that'll take a long time. So we'll tell it what portion of our data set do we want it to calculate the gradient using each time. The number of epochs is essentially the number of times that the algorithm sees our entire data set, and that roughly corresponds to the number of steps that it's taking towards the minimum. And momentum is something that we're not going to use today, but is useful to know about. It effectively, if it's going in a certain direction towards a minimum, and then it encounters a local minimum that's not the lowest minimum, the global minimum, it might get stuck in there. But if we give it momentum, as the name implies, it can kind of like push through and get to an actual global minimum. And this GIF right here is so all these trajectories kind of start at the same point, and they are all trying to reach the minimum, which is at the star. And a couple different optimizers result in different paths from that random initial point to the minimum at the star. Today we're going to be using one called Atom, and I don't know which one that corresponds to, but the one I was just describing, gradient descent, is this SGD, stochastic gradient descent. And that red one, you can see it kind of like is going very slowly while the other ones get there faster. So we're not actually going to use SGD today. We're going to use another one called Atom that is the same basic premise, but it's just has been worked on more and will work faster and better. And so that's all I'm going to cover in the slides for now. We're going to get to work on the code, but first, I just want to check if anyone has questions on the slides so far. I know I like rushed through a lot of stuff. Okay, if not, always you can feel free to send anything in the chat or to the email that Emilio sent earlier. But I'll close this for now and we'll get started on the code. So if everyone could go to this GitHub page and again, scroll all the way to the bottom where workshop 5 machine learning is, and then open the attendee version of the code that we're going to work on. It should open up this window, and then we're going to go to these 3 dots next to edit my copy and press create new copy. And then you're going to have yeah.
Oh, sorry. Do you want to just pause there for a sec just to make sure everyone can can get their own copy there? If anyone's having problems, just shout it out, and we can figure out what needs to be. All right, I think you can keep going along. If anyone has any problems, of course, like Luke said, use the chat.
Okay. So if everyone's good, this is Kaggle. If you haven't seen it before, it's just like Emilio can talk more about it later, but basically you can just write code in Python and have it compile online, and you can share your code with other people and collaborate and things. So this is a notebook that I've already prepared that you can go along and fill in. If you scroll down, you'll notice there's a bunch of these commented fill in with a number. And those are the places like that we're going to type code ourselves today. And those same markers are on the instructor copy if you want to see where we are between those two copies and like know what to fill in. So back to the top of the notebook, this block of code here is just stuff that Kaggle will automatically include for you as soon as you open a new notebook that we're just going to leave here because they can be useful for data science in general and just different like basic math things. So getting started with the second block of code, this is where we're actually going to bring in the breast cancer data set that we're going to be working with today. So this data set is from sklearn, and there are 212 examples of malignant tumors and 357 benign tumors, each which has 30 attributes. And based on those 30 attributes for each tumor, we're going to be able to predict, is it benign or is it malignant with our neural network today. And you can link to there's a link to the documentation for this data set here. So first we're going to bring in the data set. We're going to do that for this fill in one, we're going to type from. And if anyone here is new to coding, just so you're aware, syntax and spelling and everything is really important in code. If you have a letter different or spacing different or something capitalized or lowercase, that shouldn't be, it's not going to compile correctly. So make sure you're typing exactly what I'm typing. So we're going to type from sklearn dot datasets. And from there, we're going to import load underscore breast underscore cancer. And that's just the data set that we're going to work with today. And these should all be lowercase. And then with that data set, we're going to assign that to a variable. So we're going to create a variable called BC data for breast cancer data equals that load underscore breast underscore cancer. And then we're going to have open close parentheses. So this is like a function that will output that data set and assign it to the BC data variable that we've created. So once we have that, we'll go down to this fill in 2, and we're gonna just quickly visualize what this data set looks like to get a sense of what's happening. To do that, we're gonna type td.dataframe, where the D and F are capitalized. And then this function takes a few different arguments. The first argument is what is the data set that we're using or that we want to visualize. So we'll type data equals BC data dot data. So BC data is the overall data set. If we have BC data dot data, that's actually like the 212 malignant tumors and 357 benign tumors. And then there's other parts of BC data that involve like the name of each attribute and other like extra information that you might need. The second argument for this function, we'll separate by a comma, and we'll type columns equals BC data dot feature underscore names. And that will label the columns and what we're about to do. So if you go to the left of the code block, there'll be this play button to execute the cell. If we click on that, if we haven't made any typos, which it appears I have.
Luke, I think you just forgot to run the very first cell that Kaggle automatically adds.
Yes. So go if you haven't done that, run the first code block and then run the second code block. Okay, so now we see this big table. There are 569 rows corresponding to each tumor, and then there should be 30 columns that are each labeled by the name of that attribute, and then each tumor has some value for that attribute. So like the first tumor has some mean radius of 17.99, and we can see those values for all 569 tumors in the data set. So this is what we're going to be working with today. So moving on to the next code block. This is already filled in for you. There's nothing to type here, but we're going to import the Keras library, which is, it just makes machine learning super easy. It's one line of code to create a whole layer in your neural network, as opposed to if you were to do this kind of like at a lower level, like just like raw creating a neural network, it would be a lot more code. Keras just makes it super easy. So we have different parts of the Keras library that we're going to use in this block. So we'll just run that really quickly so we can use it later. Okay. And then down to the next code block. The next thing we're going to do, like I mentioned in the PowerPoint about pre-processing data, one of the techniques we're going to use is splitting it into testing and training sets. So to do that, there's a function from sklearn that can just do that automatically for us. That's the line to import that function is already written here. The function is called train test split. And now we're going to use that under this fill in 3. We're going to call the function on our breast cancer data set and assign the values, so the resulting training and test sets, to new variables. So let's first write down what those variables are going to be called. So the input data for the training set, I'm going to call x_train, and then the corresponding, or rather the input data to the test set, I'm going to call x_test. And then the output for both are going to be y train and y test. And then we're going to assign to those 4 variables the output of train_test_split. And then the first argument of this function, these should all be lowercase. The first argument is going to be our data that we're using, so bc data.data. And then the second argument is going to be the output for that data. Is it benign or malignant? And that's going to be called bc data.target. And then we just have to tell it what % of the data we want to be our test set. So we'll say test_size equals 0.3 for 30%. And then we'll give it a random seed by typing random_state equals, and we'll type some random number 42. And the purpose of that is if you're to run this whole notebook of code again, we should get the same results if we use the same random seed, as opposed to randomly having different results every time. This will just give us some more consistency. So if we run this block, that should just run, there's no output, but that splits up the data for us. Okay, and then in the next block of code, we're going to look at what our data looks like just without having done anything to it. So let's print an element of the output data on for our training set, and use 2 square brackets, and just choose a couple of those tumors. So we'll choose the 1st, 5th, and 6th one just randomly. And at that point, let's run this block and see what that data looks like. So we can see that the first tumor has the value 1, which I believe meant it was benign. And then the second one is malignant, and the third one is benign. Or I guess rather the first, fifth, and sixth one. But what we want to do is when we're working on our neural network, for each tumor, we want to have a score for how likely it is to be benign and a score for how likely it is to be malignant. So we want to split up this output data into 2 values. So if it's for sure benign, we want it to be 1, 0. Or if it's malignant, it should be 0, 1. So we want to kind of reformat our data in that way. So we'll have a line of code to do that. So let's reformat our y_train variable using this function called toCategorical. And then the argument of that function is just the data that we're reformatting, ytrain. And we'll do the same thing for our output test data, toCategorical y test. And if we then look at what the output data looks like after applying this toCategorical function, we can again print ytrain, and using 2 square brackets, we can look at the first, fifth, and sixth data points or tumors again. If we run this block of code, I've again typed something wrong. If anyone sees it, feel free to call it out. Otherwise, I just need to look for a second.
Could you scroll down just a little bit more? Oh, it may not have brought in toCategorical. Did you make sure to import it? I think it might still need to be imported.
Huh. Was that line not in here somewhere?
Yeah, I guess it didn't make it in there.
Must have got deleted.
Sorry about that. Here. So it's from keras.utils. UTILS, import, and then the function toCategorical. And then we can just pause there for a second so that people can write that in. Sorry about that, folks.
So yeah, we used this toCategorical function without ever importing it. That line was definitely in there like yesterday, but I don't know what happened to it. So now everything should hopefully run. So we can see now that instead of a 1 for the first tumor, it has 0% probability to be malignant, 100% probability to be benign. And then similarly, we have a 2-component vector for each tumor. That will be easier for our neural network to train on. Cool. So the next thing we're going to do is continuing to work on pre-processing of our data. We're going to normalize the values so that everything lies within a smaller range, somewhere around 0 to 1, as opposed to just like a super wide, crazy range of different numbers. So first, we already have this function imported called standard scalar that we're going to use. But first, at this 7th spot to fill in, we're going to look at first using print what our data looks like now, our input data, so that we can see how it changes. So the input data for the training set is called xtrain, and we'll look at the first tumor. And then let's just run that now to see what that looks like. It has 30 components, 1 for each attribute. And we can see it's kind of just a bunch of crazy numbers. I mean, you can look at that more closely if you want. There's just, without looking at the names for each attribute, it's hard to interpret. But basically, there's a lot going on. And we're going to normalize this so that there's a nicer range of values. So we'll do that under the fill in 8 by typing xtrain equals standard scalar, and this is a function, so we use open and close parentheses, dot fit underscore transform, and we'll call that on the training data. And then let's do the similar thing for the test data. Xtest equals standard scalar, open close parentheses, dot fit transform xtest. Once we have that, we can look again at what our data looks like now and see how it's been rescaled. This will shift the mean value of our data to 0 and the standard deviation to 1. So it'll just shift it to nicer values. So we can print, again, the input training data in the first tumor with 2 square brackets. If we run it now, you can just compare the new values. There are some negative values now. They should be about half negative, half positive, and they like the mean is 0 and the standard deviation is 1. This is just going to be a lot easier for our neural network to train off of and increase our accuracy with fewer steps. So if everyone's good with that, we'll move on to the next code block. Feel free to interrupt me at any time or just send your questions in the chat. So now we're going to build the actual neural network. Go away, sidebar. Okay, to create the model, we're going to first define a variable, just call it model, and we'll assign its value something called sequential, which we imported already from the Keras library. This is just a type of neural network structure that is just the simplest kind. It's just a series of layers as opposed to, there are more complicated architectures that you can use for neural networks. This is just the simplest one. We have a pretty simple data set, so this is all we'll need here. And then what we're going to do is, to this model, we're going to add a layer. We're going to add our first input layer. And there are different types of layers that you can add with Keras, but the simplest one, which is just a series of nodes, that's called a dense layer. And there are a few arguments that we're going to tell it about the dense layer we want. We want it to have 30 nodes corresponding to the 30 attributes of each tumor. And because it's an input layer, we're going to tell it input dot or underscore dim for dimension equals 30 as well. And then we're going to also tell it which activation function we want to use. And the one we're going to use is called ReLU, R-E-L-U, in single quotes. And if you remember from the slides, that function just looks like 0, and then it becomes linear. Or I guess for you guys, it would look like that way, because everything's like switched. But that's our first layer. So super easy, just one line, and you get a whole layer in your neural network. Keras is awesome. We can add a second layer to add a little complexity to the model. This will be our hidden layer, and it will again be a dense layer with 30 nodes. You can adjust this number. We just chose 30 again. And then we'll also use ReLU as our activation function. ReLU just works really well. There's a lot of theory around that I don't know, but ReLU is generally a good way to go for simple neural networks. And finally, we'll add our output layer. So model.add, again, another dense layer, but this time, instead of 30 nodes, we'll only use 2, one for the probability of being malignant, one for the probability of being benign. And our activation function this time will not be ReLU, it will be sigmoid, S-I-G-M-O-I-D. That was that S-shaped function. The reason for that is it maps really well to probabilities because it ranges from 0 to 1 and it's monotonic. So if a value is lower than another value, it will still be lower than that value once sigmoid is applied. So yeah, that's our neural network. Now what we're going to do is called compiling the neural network. So this tells it what kind of optimization procedure do we want it to use to train the neural network, and what loss function do we want to use. So the function for that is model.compile. And first we're going to tell it what loss function we want by typing loss equals, and then with single quotes, the one we're going to use is called binary underscore cross entropy. And that's used for binary classification problems. Like here we have two categories that we're assigning things to. That's called binary classification. And the optimizer that we're going to use, I mentioned earlier, is called Atom. I don't know how it works. It's complicated. It's analogous to gradient descent and it works really well. We're just going to take it and use it. And the last argument we'll use is metrics. And this is just like, what do we literally want to have it display on the screen so that we know how well it's working. And the only thing we really care about for this project is the accuracy. How accurately it's predicting whether tumors are benign or malignant. But anyway, we can get a kind of a visual of what this neural network we've just created looks like using print. And then we're going to print model.summary. And this is a function, so we have open close parentheses. And if we run this code block, I didn't make any typos. If you did, you can check my screen right now, or you can check the instructor copy of this notebook. But we get this visual. There's a row for each layer, and each layer is given a name, dense because we've chosen dense layers. And then it will tell us the shape of the output of that layer, which the first two had 30 nodes. The last one had 2 nodes. And I think the number of parameters corresponds to the number of edges between that layer and the next layer. Yeah, so that's just a nice little summary of the model we've just created. And now that we've created that structure for our neural network, chosen our loss function, and chosen our optimizer, we can go on to actually give it the data from the breast cancer data set and assign values to the edges.
Sorry to interrupt, but
yeah,
it's giving me an error. Apparently sequential doesn't exist. Did you import something before?
So this sequential was imported all the way back in this importing Keras block. There should be this line to import sequential. So I guess you can double check if you ran this block.
Okay.
If that's still not working, you can send a chat to Amelia or Paul or Archana. But I'll keep moving for now. So on to fitting the model to the training set. So we're at the 13th fill-in marker. So what we'll type here is model.fit. And then the first argument is going to be the input data that we're fitting, which we called xtrain. The second argument is that corresponding output data, ytrain. And then we're going to assign values to a couple of the hyperparameters that I talked about in the slides. The first one is called batch size, batch underscore size. That's the number of data points that it's seeing each time it calculates the gradient. And we'll just give that 100, which is like a fifth of our overall data set, I think. So that'll just make it go a little bit faster. The epochs is how many times it sees the whole data set, and we'll just also say 100. That's effectively the number of steps it takes on the loss function towards the minimum. And then the last argument is called verbose, and you can assign like a 0, 1, or 2 to verbose, and that just is like how much information you'll see on the screen as it's fitting the model. If we choose 1, it'll show us like a loading bar, and then it'll tell us the loss and the accuracy at each epoch. So each time it's seeing all of the data. And if we run this block, we'll get a whole bunch of stuff come up. We'll have about like 2 rows for each epoch. So you'll see at the very beginning, it's assigned a random weight to each edge, and it has not great accuracy, not terrible, about of 84%. And then it's going to start taking steps towards the minimum, and it should be increasing as we scroll down. There should be about 100 rows. There's even another window of the outputs. By the 100th epoch, we can see it's gotten all the way to 98.9% accuracy, which is really awesome. But this is accuracy on the training set. So another question we want to ask is, when the neural network sees new data that it's never seen before, what will the accuracy be then? And that's what we're going to determine in our next block of code. Before I move on to that one, does anyone have any questions about building the neural network or compiling or fitting the training data, conceptual or like syntax-wise or errors or anything? And feel free to tell me to slow down or anything. I'm just like talking a mile a minute. So, but if everyone's good, I'll move on to the next block of code here. So at this 14th fill-in marker, what we're going to do is evaluate the accuracy of our model on test data. So we'll create a variable called eval results, and we'll assign to it, we'll call this function model.evaluate from Keras. And the arguments are the input test data, x test, and then also the output y test. And then there's a verbose argument that we'll set to 0 because we don't need to see anything here. And what this is going to do is tell us the accuracy on the test data, which we can just run, and it'll just spit out that number. And it gives us a value for the loss function, which is pretty close to 0, and then an accuracy of 98.25%, which is really good. It's not always this easy for sure. We've created a pretty simple neural network and gotten really high accuracy pretty quick, just because this is a really simple data set. But in the real world, you'll have to mess around with the number of layers, the number of nodes, the activation functions you're using, all your hyperparameters. But this data set's super easy, so we got a good result pretty fast. Now what we can do is actually like see what the process would look like if you're doing research, you have a tumor, you measure these 30 attributes for it, and then you want to make a prediction, is this benign or malignant? So what we'll do is, as an example of this, we'll look at one of the elements of the test set. So we'll create a variable pred1 for prediction 1, and assign to it model.predict. And then we'll take a couple elements of the input for the test set and use 2 square brackets to select the 1st and 7th tumors just randomly. And then we can print, we can print here the value of that variable. And then we can also print here what actually is the output for these tumors. Are they actually benign or malignant? because we already have that data in y test. With 2 square brackets, we can again select the first and 7th tumors and compare. So if we run here, we see that for the first tumor, it has 0.999% chance of being, I think this one is malignant, and then pretty close to 0 chance of being benign. And it turns out that matches really closely the actual known output, which is 1, 0. And the second prediction is pretty similar. It has a 99.4% chance of being malignant when it actually is malignant. So these are good predictions. This is what we want to happen. And that's the end of this notebook. So I have a few more slides to talk about in the PowerPoint about how to develop your neural networks further and diagnose where your problems are happening and how to fix those problems. So I'll go back to those in a moment if nobody has questions on these last few steps. All right, so moving back over here. So the 2 biggest issues that we have in machine learning are called overfitting and underfitting. And how this kind of works is illustrated with these 3 plots. So if you have some set of data, you could pretend these dots are each a tumor, and if it's filled in, it's benign, and if it's not filled in, it's malignant. And we want to draw some kind of line that will divide up the data. And if a new data point is on one side of the line, we can predict that it's benign. On the other side, it's malignant. So if we have a really simple model, we might just draw a straight line like this in the furthest left diagram. And that works kind of well, but there's like maybe like 7 data points on the wrong side on this side, and then 1 on the wrong side here. It's not super great. We can do better. So moving to the optimal model, if we add a little complexity and make it kind of this circular shape, we only have 1 wrongly categorized data point on each side, which is a lot better. If we go even further and add a lot of complexity to our model, we can draw this really wacky line, which works 100% on all of the data we've given to it. But we can kind of see this is not really the actual trend that's happening. The actual trend is this kind of circle shape. So if we were to give new data to predict on, it wouldn't predict so well because it's fit too closely to the training data, while we want it to generalize well to any new data that it sees. So these 2 problems are called underfitting and overfitting, respectively, and they also have the names bias and variance. So we want to know how to figure out which type of behavior our model has and how to fix that. So a plot of how this works is this orange line is the error on new data, and the red line is the error on data that it's already seen, the training error. And then the x-axis is the complexity of the model, and the y-axis is the error. So with very, very little complexity, any data will have high error because we haven't trained the model yet, or we haven't given it much capability to predict well. As we increase the complexity more and more, the error on any data will decrease to a certain point, but then eventually the test data will start to have more error because it'll start to overfit to the training data. So the training data error will continue to go down while the generalization error will start to go up. So these 2 zones are called the underfitting zone or the overfitting zone. And depending on which side we're in, we want to move closer to this optimal point. So to do that, we can look at something called learning curves, which there are functions from sklearn that you can call for your neural network that will produce these for you. which you can look up documentation for. But so if you see one of these plots, you can look at it and figure out, do we have underfitting or overfitting? And another word for that is low variance or high variance. So this left case is underfitting or low variance. And we can see that the test error decreases and gets very close to the error on the training data with a large training set size. So if we increase the size of the training set, we'll see that the respective errors get very close to each other with this small gap. That means that there is underfitting going on, while there will be a much larger gap for overfitting. So you can make these plots and see how large that gap is, and then change your model complexity accordingly to address that issue. So you can decrease the number of layers or add more layers, increase or decrease the number of nodes, things like that to address the generalization of your neural network. And then this last slide, I just have 4 links here. You can read more about the conceptual aspects of machine learning, some of the math behind it, the documentation for Keras, which is the library we used for machine learning, in applications to medicine that were actually really cool. It talks about like how IBM uses machine learning for medical applications, how it's used in clinical trial research and drug production, and like personalized medicine and a bunch of applications like that.